Can you spot cycles before they wreck a project? Course Schedule is a Pattern Mastery 100 classic. Frequently asked at Google, Amazon, and Meta for its blend of graph, topological sort, and cycle detection. Over 40% of candidates either miss edge cases or get tangled in the graph logic. If you master this, you'll ace any dependency or order check problem in interviews. Let's break down Course Schedule with the basic method, a stepwise approach that builds deep understanding for any cycle or topological ordering question. Let's break down the problem. You're given num courses, number of courses, and a list of prerequisite pairs. Can you finish all courses? Each pair, A, B, means, to take course A, you must first finish course B. The courses form a directed graph. Your task is to check if there's any cycle, which would make it impossible to finish all courses. Integer num courses list of prerequisite pairs. Boolean. True if all courses can be finished, false otherwise. Think of project tasks or college courses, where some steps must happen before others. Interviewers might ask, how would you check for circular dependencies in a build system or workflow manager? What's tricky? You need to detect cycles in a directed graph, classic topological sort. Multiple valid orderings may exist. Must efficiently track visited nodes and recursion stack. Build an adjacency list to represent course dependencies. Use DFS to detect cycles. Mark each node as not visited, 0 visiting, 1 visited, 2 for each node. If already fully visited, skip. If visiting, and you re-enter it, you found a cycle. Recursively DFS all neighbors. If any cycle is found, return false. Otherwise, return true. Let's clarify. The recursion stack, visiting, is key. It tracks the current path. Alternatively, BFS, Kahn's algorithm, with indegrees works as well, but DFS is easier to explain in interviews. Edge cases. No prerequisites, always return true. Disconnected graph, some courses with no dependencies. Multiple cycles. Build adjacency list from prerequisites. Initialize state array for all nodes. For each node, DFS. If node is visiting, return false, cycle. If node is visited, skip. Mark as visiting. DFS all neighbors. After neighbors, mark as visited. If no cycles, return true. Let's try to implement it using solution 1. This line just starts a new blueprint called solution. Think of it like naming a folder that will contain our function for checking if you can finish all the courses. Here we define a function called canFinish. It takes in num courses, how many total courses there are, like 0 to num courses 1. Prerequisites, a list of pairs that say to take this course, you must do that course first. This function will return true if it's possible to complete all courses, or false if there's a cycle, like a loop in prerequisites that makes it impossible. This line builds a graph using a dictionary. Graph is like a map where each course number, I, is a key. Each key starts with an empty list, which will hold the courses that depend on it. So we're saying, for every course from 0 to num courses, 1, create an entry in graph with an empty list. From a time complexity perspective, this takes O num courses because we loop once over all courses. Now we loop through each pair in prerequisites. Each pair is like course, prereq, meaning you must take prereq before course. We're going to use these pairs to fill in our graph. The number of these pairs is usually called E for edges, so this loop runs in OE time. For each prerequisite pair, we go to graph prereq and append course. In plain language, from this prerequisite course, you can go to this next course. We're building edges in our graph from prereq course. This lets us later walk forward and see which courses depend on which. Overall prerequisites, this line contributes to OE time. Here we create a list called visited with 1 entry per course, all starting as 0. We'll use this like a status flag. 0 equals not visited yet, 1 equals currently visiting in the recursion stack, 2 equals fully processed, done visiting all its neighbors. This helps us detect cycles. If we ever see a course marked 1 again while exploring, it means we've gone in a loop. Creating this list is O num courses. Now we define an inner function called DFS, short for depth first search. This function will try to explore from a given course to all the courses that depend on it, walking forward in the graph. It will help us detect if there's a cycle. First check, if visited course is 1, it means we are currently exploring this course and somehow came back to it again. That's a sign of a cycle. So if we detect that we hit a course that's already being explored, 1, we immediately return false from this DFS call. Next check, if visited course is 2, it means we have already fully processed this course before, and we know it's safe, no cycle down that path. In that case, we simply return true. We're saying, from this course onward, we already confirmed that there's no cycle. Now, we mark the current course as 1, meaning, we are currently visiting this course. Now we loop over all the next courses that depend on this course. Graph course is the list of courses that you can only take after finishing this one. For each NXT, next course, we call DFS NXT to explore it. If DFS NXT returns false, it means starting from that next course, we detected a cycle. So not DFS NXT will be true in that case, and we'll react to it. So DFS course being true means this path is safe. Outside the DFS function, we now loop over every course I from 0 to num courses 1. We do this because the graph might not be fully connected. There could be separate groups of courses. We want to make sure we check all of them, not just one starting point. This loop runs onum courses times, but remember, thanks to the visited list, each course's DFS work is effectively done once overall. For each course I, we call DFSI. If DFSI returns false, it means we detected a cycle in the component that contains course I. Not DFSI will then be true, and we know it's impossible to finish all courses. In that case, we immediately return false from the can finish function. This is the final answer. No, you cannot complete all courses, because there's at least one cycle in the prerequisite graph. If we finish the entire loop without ever seeing DFSI return false, then it means no cycles were found anywhere in the graph. So we return true, meaning, yes, it is possible to finish all the courses given these prerequisites. Overall, the time complexity of this algorithm is OV plus E. V equals num courses, E equals number of prerequisite pairs. We visit each course and each prerequisite at most once in the DFS process. And that's how this algorithm works. It first builds a graph and a visited status list to represent all the courses and their dependencies, then uses depth-first search to detect any cycles in the graph. Efficient, simple, and elegant. Alright, let's walk through this test case and make sure our solution behaves exactly the way we expect. We're given two courses, that means course 0 and course 1. And the prerequisites array, 1, 0, tells us one simple rule. To take course 1, you must first complete course 0. That's a clean, straightforward dependency chain. And importantly, there's no cycle here. Throughout this entire check, we never revisit a course that's already in the visiting state, which means, no cycles. And the program prints true, which matches the expected result. Perfect. So yes, our implementation is correct. The algorithm detects that there are no cycles in the prerequisite chain, meaning all courses can be completed. Simple input, clean execution, accurate result. Now let's try another implement approach using solution 2. This line begins our class solution, which simply wraps everything together neatly. Think of it as the container for our more optimal approach. Here we're defining the function can finish again, but this time we'll use a topological sorting approach. This method is often faster and cleaner for detecting cycles. We start by building a graph, same idea as before. For every course from 0 to num courses 1, we create an empty list. That list will store courses that depend on the current course. Here we create an indegree list. Indegree I will tell us how many prerequisites course I has, basically how many doors are blocking it before you're allowed to enter. Now we loop through every pair in the prerequisites list. Each pair tells us, to take course, you must first complete prereq. This loop will take OE time. This line says, starting from the prerequisite, you can move forward to the dependent course. This is the heart of the topological sort approach, tracking how many prerequisites each course has left. This line gathers all courses that have 0 prerequisites, indegree equals 0, and places them into a queue. We initialize count to 0. This will track how many courses we've successfully completed in our topological process. Now we begin a loop that continues as long as our queue isn't empty. This loop is the core of topological sorting. Each time a course becomes available with no remaining prerequisites, we process it. We remove a course from the left of the queue. This is now the next course we can take. No prerequisites blocking it anymore. We increment count to mark that we have now completed this course. It's like checking off one box in our course completion list. Next, we look at all courses, NXT, that depend on the current course. For each dependent course, we reduce its indegree by 1 because one of its prerequisites has just been satisfied. If you imagine these as doors, this line is effectively unlocking one of the locks for NXT. Here we check, has the dependent course now reached 0 prerequisites? If so, it means all its requirements are completed. It's ready to be taken. And if it is ready, we add it to the queue so it can be processed next. This is like moving it into the "you are free to take this course now" list. Finally, after processing everything we can, we check if the number of completed courses equals the total number of courses. If count equals noon courses, it means we were able to complete every single course, no cycles existed. If not, it means some courses stayed locked forever, which only happens when there's a cycle blocking progress. So the entire method runs in OV plus E, time, very efficient. And that's how this algorithm works. It first builds a graph and counts each course's prerequisites, then repeatedly removes courses with 0 remaining prerequisites using a topological sort. Efficient, simple, and elegant. Let's test our function using this input, 1, 0, 0, 1. These pairs represent course dependencies. Each, A, B, means you must take course B before taking course A. Now here's the interesting part. The pair, 1, 0, says 0, 1, and the pair, 0, 1, says 1, 0. So as soon as we build the graph, we can already see a loop forming. Running the algorithm, our indegree array shows that each course has a prerequisite, so nothing starts with indegree 0. That means our queue begins empty, and no courses can be processed, a clear sign of a cycle. And that's exactly what our program outputs, false. We expected false, and the result matches perfectly. So, our implementation is correct. The algorithm successfully identifies the cycle in the prerequisites and confirms that the student cannot finish all courses, efficient, accurate, and reliable. Let's have a quick recap. We're given a number of courses and prerequisite pairs. Each pair means take A only after B conceptually. That's a directed graph. The question is simple. Does a cycle exist? If yes, you can't finish. If no, you can. To decide, we compared two classic approaches, DFS with state marking versus BFS using Kahn's algorithm, indegrees. DFS is interview-friendly and direct for cycle detection. Kahn's is an equally valid alternative. Key pitfalls: remembering multiple valid orders can exist, handling disconnected nodes, and not missing edge cases like no prerequisites. Plan of attack: build an adjacency list from prerequisites. Track each node state, unvisited, visiting, visited. For every course, run DFS. If we ever re-enter a visiting node, that's a cycle. After exploring neighbors, mark the node visited. If no cycle is found anywhere, all courses are doable. We set up the graph and the state tracking, walked each node with DFS, and short-circuited as soon as a cycle appeared. The code ran on LeetCode cleanly, no errors. We verified the logic by running through simple passes, like a single chain, and clear failures, a two-node cycle, plus edge cases such as empty prerequisites and disconnected components. The solution behaved as expected and passed the LeetCode tests. The takeaway: cycle detection is the heart of dependency problems. If you can model constraints as a graph and reason with visiting versus visited, or indegreed appeal layers, you can reliably untangle any ordering question under interview pressure.